Well, I would like to start, of course, just by thanking the organizers, Jeremy and Yoav, Matt and Edmund, for inviting me for this. It's a great honor. Just to indicate that, everybody that knows me will know that putting on a button-down shirt and actually ironing it this morning, is a real chore. I pretty much never do that except for really special occasions like, weddings, restaurants with 2 or more stars, something like this. So anyway, so I really appreciate the invitation and the opportunity to talk to you today about, contact submanifolds in high dimensions. So this is a relatively new area of study. A lot of people probably know. We knew very, very little about contact geometry in higher dimensions up until a few years ago. And there's been many, many breakthroughs due to several people that are going to be in the audience here. So we're really starting to get a little bit better picture of what's going on there, but we still don't know most questions you would ask me about high dimensional contact manifolds. We don't know. So recently, last year or so, with a few other people, I've been trying to understand submanifolds of contact manifolds in high dimensions in the hope that they'll help us understand those manifolds through constructions, through properties, and so on. And I wanted to start these lectures by trying to indicate to you how submanifolds of contact manifolds really can help you understand contact geometry. And in particular, I'm going to focus just in this first talk on the 3-dimensional case that we actually understand quite a lot about. And I'll kind of show you that if you go through the history of contact geometry, almost every major advance up until maybe the late 90s, that might be a slight exaggeration, but more or less most major advances in the subject were done by studying transverse knots. I think a lot of people getting into the field now don't realize that because there's other perspectives, more modern perspectives that people tend to focus on. But I do think transverse knots not only gave birth to a lot of what we know about contact 3 manifolds, there's still a lot of things that they might be better suited for now than say, the Legendrian or other sorts of submanifolds. By the way, I don't mean to disparage Legendrian submanifolds. I love them. I study them quite frequently. And they'll actually be appearing here and there throughout the talks as well. So I don't want to kind of forget that. In fact, I was planning on having a couple lectures to focus on the Legendrian picture as well. But then I realized I started writing things. There was no chance that I was going to be able to say the other things I wanted to and get to those as well. So we're going to really focus on the kind of transverse or contact submanifolds of contact manifolds picture. Anyway, with all that said, I also wasn't exactly sure of everybody in the audience, so I wanted to kind of start with the basic definitions to set the stage so everybody's on the same page here. So starting at the beginning, what is a contact structure? So a contact structure is, well, the quick way to say it is a maximally non-integrable hyperplane field on an odd dimensional manifold. Okay, you hear those words, and unless you've heard them before, it probably means nothing to you. So let me tell you geometrically what that should mean to you. It's what's here kind of in orange. So maximally non-integrable, it turns out that if you give a distribution, so basically a hyperplane field just means at every point in the tangent space, you've got a hyperplane. So you should think of it kind of, everybody's very familiar with vector fields, right? So at a vector field on a manifold, at every point, you've picked out a tangent vector. And as you move from point to point, that vector might change in some smooth fashion. Well, hyperplane field is very similar. At every point, I picked out a hyperplane. And as you move from point to point, that hyperplane can change. And it turns out that if you have a hyperplane field in a manifold, you can always find submanifolds of your manifold that are tangent to it if those submanifolds have low enough dimension. So if you play around a little bit with kind of the geometry of what's going on here, you can see that if you have a 2n-dimensional plane field, that you can always find submanifolds that are tangent to it of dimension n and less. But in some situations, there are some examples of hyperplane fields where you can't find anything of a bigger dimension. So if you have a submanifold of dimension bigger than n, again, when we've got a 2n-dimensional hyperplane and a 2n plus 1-dimensional manifold, if you have a manifold of dimension bigger than n, it will never be tangent to that hyperplane on an open subset. So that's what maximally non-integrable means. It's as non-integrable as it can be. So it can't be completely non-integrable, but it's as non-integrable as it can be. So a little caveat throughout the whole lecture series is pretty much whenever you've got a word, a mathematical word that you can put oriented in front of, do so. I won't always remember to do that when I'm stating my theorem sometimes, but if I have a manifold, it's going to be oriented. If I have a hyperplane field, it's going to be oriented, and so on. Now, these are not essential assumptions. You can try to understand the theory where you look at non-orientable things as well. It's quite interesting, but it's just not something we're going to talk about here because it adds another degree of complication that I'd prefer to avoid on our pass in these next couple of days. Anyway, so it turns out if you have an oriented hyperplane field in an oriented manifold, you can always find a one form such that the kernel of that one form, right, a one form at every point in the tangent space is a linear map from the tangent space to R, so its kernel is typically, if it's non-degenerate, is going to be a hyperplane. And so you can describe your hyperplane field as the kernel of a one form. And basically that hyperplane field will be contact if and only if this condition is satisfied. Alpha wedge d alpha to the n is positive. Well, what does positive mean? Remember, our manifold is oriented. That means it has a preferred class of non-zero 2n plus 1 forms. And this is in that class. So basically kind of the volume form on the manifold. It's a positive multiple of the volume form defined in the orientation. So that's what that means. So it's not obvious that this condition is equivalent to this condition up here, but if you play around with the Frobenius theorem, you can actually work that out without a great deal of trouble. So the first kind of canonical example of a contact structure is just on Euclidean space, R2n plus 1. You can just look at the kernel of dz plus the sum of R. My first typo. So you're going to probably find 1,000 typos as we go through this. I'm sorry. And this is not only a typo, it's a matho. There's supposed to be a square on that, Ri squared d theta. OK. All right. So we can actually draw a picture of that, at least say in dimension 3. So when n is 1. So notice when r is 0, you just got dz. So all your hyperplanes are just perpendicular to the z-axis. And now take any ray perpendicular to the z-axis. As you move out along that ray, notice the vector tangent to that ray, the r coordinate, is always in your hyperplane field. So your hyperplane field is always tangent to the axis that's perpendicular to the z-axis, or the ray. And as you move out, the plane starts to tilt. And it tilts 90 degrees, or pi over 2, in a left-handed fashion if you carefully work that out. So this is kind of the canonical picture of a contact structure. And in fact, there's a wonderful theorem called Darboux's theorem that says every contact structure is locally equivalent to this one here on R2n plus 1. So if you're on a 2n plus 1 dimensional manifold, and you have a contact structure, every point has a neighborhood that looks like a neighborhood of a point here in Euclidean space. So that's another way you can interpret a contact structure, is you can interpret it as saying it's a hyperplane field that locally looks like this. So if you understand this picture, you at least locally understand what a contact structure is. So I've been staring at this side of the audience. I think I'm going to move over here for a while, stare at this side for a while. Okay. All right. So that's your first example. And again, if you understand this example, you at least have a local understanding of contact geometry. So one other example I want to give, because it turns out I'm typically going to be more interested in compact manifolds than non-compact manifolds, like most topologists are. Oops, too far. If you compactify R2n plus 1, you get a sphere. And that sphere you can think of as the unit sphere in complex space. And then you can define a contact structure as just the complex tangencies to the sphere. And so you can write it in various different ways. I've given you several expressions of it there. Another way you can describe it, I was just running, you can say I've crammed a lot on each slide. I didn't want to cram another line. But you can also say if you have the sphere, there's this natural Hopf vibration of the sphere, right? Anytime you have an odd dimensional sphere, you have the Hopf vibration. These are just the orthogonal complement to the Hopf vibration. It's another way to think about it. And I wanted to emphasize that if you have the one sphere, right, that's just the unit sphere in complex space, that is actually a contact manifold with the contact structure being the 0 vector at every point. Most people don't think of the S1 as actually being a contact manifold, but it is. And it's one of the easiest situations where you can classify contact structures, right? There's one. It's just 0 at every point. Great. So throughout these talks, the main thing we're going to be considering is contact embeddings. So what do I mean by contact embeddings? So there's a condition that you might not think of a priori, but you really do need it. So if I have one contact manifold M(x)y and another one M prime xi prime, a contact embedding is simply a topological embedding such that it's transverse to the hyperplane field, just in the standard sense of transversality, and such that the contact distribution xi by your map, another typo. Of course, you can take dE, so it works on the tangent space, right? So that the map sends the contact hyperplanes for the first manifold into the contact manifolds for the second manifold. Another way to say that is if you had a submanifold of M prime, You would call it a contact submanifold if it's transverse to the contact hyperplanes, and the induced hyperplane on that manifold is a contact structure itself. And so a contact embedding is simply an embedding such that its image is a contact submanifold with the same contact structure you started with. And so these are the things we're going to be mainly interested in. So I should probably pause here for a second, because I tend to talk too fast anyway. But ask, is there any questions here? Because again, this is what we're going to study for the next kind of 3 or 4 or 5 talks. Well, 4 talks after this one. So let's make sure everybody's happy with the definition. Yeah, good. OK, great. Well, so we are going to be talking about this in general in higher dimensions. But for the rest of this talk, I really wanted to focus on the 3-dimensional case. So if M is a 3-manifold and you have an S1 embedded in there, it's a contact embedding. Well, the only condition really is that you're transverse to the contact structure, right? Because the second condition that the contact hyperplanes, in other words, the 0 vector is sent into the contact hyperplanes here, well, that's obvious, right? I mean, it's a linear map. 0 goes to 0. So transversality is the only condition. So the study of contact submanifolds in dimension 3 really amounts to the study of transverse knots. And that's what we're going to do for the rest of the talk here. And as I've already said at the beginning, we're going to see throughout the rest of this talk that, first of all, studying transverse knots, there's just a really rich structure there. There's a lot of interesting stuff going on. I'll talk about those kind of at the very end of the talk. But what I'm going to talk about for the majority of the rest of the talk is that many of the milestones, many of the things that really developed contact geometry as an interesting subject and related it strongly to topology came out of studying transverse knots. And as we kind of go through and I discuss kind of the history here, what I'd like you to do is kind of keep in mind how might these generalize to higher dimensions, because this is really what we want to talk about for the rest of the time. And you're actually going to see through the final 4 talks, there's probably, I'm going to ask you more questions than I'm going to give you answers. So this is a really kind of burgeoning field, and I think there's a lot of room for development. And I'm happy to talk to anybody that wants to talk more about these things and maybe help develop some of these subjects. But I'll give you a few kind of preliminary starts in the higher dimensional setting. But again, for today, let's just look at the 3-dimensional setting. And what's the first milestone in contact geometry in dimension 3? Well, the first one is the fact, the most basic thing you want, right? If you've got a manifold, you might want to ask, does it have a contact structure? Very, very basic question. And actually, you can be a little bit more refined in your question. So here's a second question that's a little bit more refined than the first one. You can ask, if you have a hyperplane field, or we're in dimension 3, so it's just a plane field. If you have a plane field on a 3-manifold, can you move that plane field around to make it contact? Right? That's maybe a little bit more refined question than just does the 3-manifold have a contact structure? And well, the answer to this is yes. And it was originally proven in 1971 by Martinet and Lutz. They were actually distinct papers. I haven't actually read the details of the arguments in the papers, but my understanding is that Martinet kind of more or less proved the existence on 3-manifolds, where Lutz managed to prove you kind of get all homotopy classes of plane field. I'm sure about the result, what I said for Lutz. Maybe Martinet did more than I thought. But anyway, so what I'd like to do is kind of indicate what's the role of transverse knot theory in this result. And this is the original way that they did it. So let me give you a sketch of the argument. So the first thing you need is this interesting fact that if you have any knot, so any embedding of S1 in a 3-manifold, so we'll call it a knot, you can always isotope it in a C0 small fashion. So in other words, preserving the knot type so that it's transverse. And this proof is actually very, very simple. Once you know Darboux's theorem. So remember, Darboux's theorem said that every contact manifold looks locally like this picture. And that says, so now if you have your knot, you can take a little segment of it and say it looks like it's sitting inside of here. And you can just explicitly, by hand, make it transverse to the contact hyperplanes. It's actually not very hard to do. There's many ways you can do that, actually. So this first fact is actually very, very easy in dimension 3. And we're actually going to see it's actually not really clear if you can do this in higher dimensions. There's ways you can try to approach it, and we'll talk about those probably tomorrow morning. But at the moment, it's an open question whether you can actually prove a similar result in higher dimensions. But still, that's the first fact we need in dimension 3. OK, second fact. Any knot has a neighborhood that's contactomorphic to a standard model. So here's a standard model I want to use, S1 cross R2, with the kernel of this being your contact structure. And forget what that says. Let me just tell you what's going on here. So you've got your S1 cross R2. And your contact structure, essentially, it's going to be perpendicular to the S1 along the S1 cross 0. And then as you move out on any ray perpendicular to S1, it's going to start rotating in a left-handed fashion, except now instead of just rotating 90 degrees, it's going to rotate over and over and over again. So as you go out along your ray, your contact planes are always tangent to the axis, and they just kind of keep flipping over. And well, OK, I can only do it once, but they flip over and over and over. OK? So you can kind of really see what's going on by just paying attention to kind of the trace of the contact structure on these kind of concentric tori going out from the S1. Right? So they have the slope that gets more and more negative. It gets to infinity. Then they go through positive slopes and so on. OK? And that happens over and over again. This is also very easy to prove. It's a slightly more delicate argument than Darboux's theorem. But if you know the right proof of Darboux's theorem, you can prove this just as easy. This also has the advantage that it's, oh, I don't need a pointer, I can point. It also has the advantage that this is actually true in all dimensions, that if you can make something a contact submanifold of a high dimensional manifold, you get these kind of local models for them that you understand very well. So these are the first two facts we need, and these are the only two facts we need about contact geometry. One of them very simple and is true in all dimensions. One of them very simple, but may or may not be true in all dimensions. The third fact we need is a purely topological fact. And it's one that probably everybody here is very familiar with. It's that any 3-manifold can be obtained from S3 by Dane surgery. Actually by real surgery, but in particular Dane surgery, on some link in S3. And so just to remind everybody, again, I'm sure you're fairly familiar with it, but Dane surgery just means remove a neighborhood of your link. So remove a bunch of solid tori from your S3, and then re-glue in solid tori by some diffeomorphism of the boundary. And this gives you some other manifold. And you can get every manifold through this process. And actually, there is some version of this that's true in all dimensions. I'll actually prove fact 3, or give a sketch of a proof of fact 3 a couple lectures from now. And we'll kind of see how there's an analogous thing that's true in all dimensions that you might try to use to prove a similar result in all dimensions. OK, so now what's the proof of this milestone that all 3 manifolds have contact structures? It's very, very simple. So given your 3-manifold M, we know there's this link L in S3 such that, from fact 3, such that surgery on it gives you M, right? Fact 1 tells me you can assume that link is transverse to the standard contact structure. Now fact 2 tells me that there's a standard neighborhood, so we know exactly what the contact structure looks like near the transverse link. Now notice the contact structure on S3, the standard contact structure on S3 gives me a contact structure on the link complement, right? Now we have these solid tori that get glued in. Well, we can actually use the standard models from fact 3 or fact 2 to extend the contact structure here over there because we know it's kind of going on near the boundary. So if you haven't thought of this before, it's maybe that was a little bit fast, but you can actually see that near the boundary here, the contact hyperplane is just doing this little bit of a rotation, and you just have to make sure you can kind of extend that into the interior of your solid tori. And that's actually very easy to do. And that's it. I mean, that's the entire proof. So it's actually quite a, I mean, nowadays, in hindsight, it's quite a straightforward proof. And one might hope to try to generalize something like this to higher dimensions. So we'll talk about that. I should mention, suppose you want to get that result where you get all homotopy classes of plane fields and not just one contact structure on every 3-manifold, but actually get ones for every homotopy class. Well, that's actually not so hard once you've studied homotopy classes of plane field, which I don't want to spend a lot of time. How are we doing here? 21. Yeah, I probably don't want to go into details about the homotopy classes of plane field, but I'm happy to talk to people about it if they would like afterwards. But there's this really simple procedure called a Lutz Twist, which means when you extend the contact structure over these solid tori, you can kind of do the minimal extension where you have the minimal amount of twisting in that solid torus. Or remember, this local model, you twist it infinitely often. So you go by slopes infinitely often. So there's actually infinitely many different choices for solid tori I can plug in from this local model on those solid tori. And if you, instead of taking the first time you hit a slope to kind of extend the contact structure, you take the second time. That's what's called a Lutz Twist. And by doing that, you can actually get all homotopy classes of plane field. And again, once you've kind of gone through the homotopy class of plane field, it's relatively easy to show that. Okay. All right, so that's milestone 1. Any questions about that? Okay. Great. Milestone 2. Oh, sorry. One other comment. I have to plug work of my students. So Jamie Conway, who's graduating this year, last year actually proved, so we proved that every homotopy class of plane field has some contact structure in it. But you might ask, can you get every contact structure on a 3-manifold through surgery on transverse knots? And that's actually what Conway had proved last year, that you can actually get every contact structure on every closed 3-manifold through surgery on S3, on some transverse knot in S3. It turns out this is actually not very, once you've kind of made the right definitions, which for some reason hadn't been made until more recently, but once you made the right definitions, this is actually relatively easy to prove based on work about a similar result about Legendrian surgery or contact surgery on Legendrian links from Ding and Geiges in 2004. And it turns out that this reinterpretation of the Legendrian surgery into the transverse surgery is more natural in some respects, especially if people are used to maybe working with Hegardt floor theory to understand contact structures. Anyway, maybe that's a cryptic comment, but since I don't want to go into Hegardt floor theory, I think I'll leave it at that and let you ask me about it later if you're interested. Anyway, so again, I want to emphasize this result just because you might ask, can you prove something like this in higher dimensions? Is this true in all dimensions? Is there various surgery operations that are like transverse surgeries or maybe a few other types of surgeries that will allow you to get all contact structures on higher dimensional manifolds? And in our fourth talk, I'll sketch an argument that says, yes, that is actually true in dimension 5. And there's at least an approach how you might try to do this in higher dimensions, but I'm not quite sure how we can do that. But maybe even if you can't just do surgery to get to everything, can you find other cut and paste constructions to build all contact structures in high dimensions? Right now, I don't think there's a good way to do it, but in theory, it could be done. All right, good. So now let's move on to milestone 2. So our first milestone was in 1971. So in 1983, the following milestone occurred. So a very natural question, once you know 3-manifolds have contact structures, you can ask, do they have more than one? Or a better question is, if you have 2 contact structures in the same homotopy class of plane field, do they have to be the same contact structure? So if they could be the same, are they the same? And the most basic variant of that question is on R3, we have this nice simple contact structure I gave you on the second slide. And we also have this other one that kind of twists infinitely often. Are they the same or not? And that's actually quite a hard question. Nowadays, there's lots of ways you can actually prove that they are different. But the original way they were proved in 1983 by Bennekin was using transverse knots. So I'd like to sketch for you how that happened. But before I can do that, I actually need a particular invariant of transverse knots that's actually quite easy to define. So if you have a transverse knot, let's assume it's null homologous. That means that it actually bounds a surface in your manifold. And it's very easy to see, it's a very easy exercise to see that if you have any plane field, like our contact planes, you restrict it to a surface with boundary, it has to be trivial. It just has to be. Any oriented plane field is trivial over a surface with boundary. But because it's trivial, I can pick a non-zero vector field in the contact planes along the surface. I can take a copy of K and push it along V. So then I have 2 knots, K and K prime, and I simply measure their linking. And that's called the self-linking number of the transverse knot. It's very easy to convince yourself that if you have 2 transverse knots in a contact structure, if they're isotopic through transverse knots, then the self-linking number will be the same. So this is an invariant of transverse knots, and you can use it to try to distinguish transverse knots. And I'll say a lot more about that later. But we need that right now for Bennekin's result. Oh, by the way, I guess I should mention here, again, every time I'm saying something, you should ask what's going on in higher dimensions, right? So is there this notion of self-linking in higher dimensions? And so I ask that question here. I say that's an open problem. And it's an open problem when I put the word really there, because it's actually very easy to make the same definition in higher dimensions. You can do it. But I claim, and I'll justify in the 5th lecture, that actually that thing that you define in high dimensions is really kind of a derivative invariant. It actually is something that's determined by something more fundamental. And we'll try to talk a little bit about that in the 5th lecture. So again, there is a generalization, but how useful is it? And should you really kind of interpret it the same way you interpret the self-linking in dimension 3? And I'm not quite so sure there is. But we'll see. We'll see. OK, good. So what's Bennekin's result? Bennekin's result is that if you have a transverse knot in the standard contact structure on R3, then, and you have a surface that it bounds, so a ciphered surface for the knot, then the self-linking number is a lower bound on the genus, well, on minus the Euler characteristic, but on the genus for the knot. So this seems, when you first see it, you don't think about it too hard. It seems like an innocuous result, but it's actually very important and very powerful. And one might wonder if something similar is true in higher dimensions. But once you have Binnikin's results, it's super easy to see that these two contact structures, the over-twisted one, so remember, which way are we going? Yeah, there we go. So the over-twisted one is different from the standard one, because in the over-twisted one, if you just look at this unknot, you can just easily compute the self-linking number as 1. But it's an unknot, so 1 is not less than minus the Euler characteristic, which is -1. So that means that the over-twisted contact structure has to be different from the standard one. And this was the first such result in the history of contact geometry, kind of distinguishing things that, at least on the level of plane fields, are the same, but are actually different. And it's distinguishing it in a very interesting way. And very quickly after Binnikin's work, Eliashberg had a couple of really impressive papers where he actually defined the notion of tight and over-twisted. So you've probably heard, if you've heard anything about contact geometry in dimension 3, you've heard tight and over-twisted. This is a fundamental dichotomy in dimension 3. And the birth of those notions really came out of Eliashberg studying and looking at Binnikin's work. So it really came out of transverse knot theory. And one way you can define tight, this is not the way that it was originally defined, but one way you can define tight is a contact structure is tight if and only if the Binnikin inequality is true. So again, you can define whether something is tight or not by using transverse knots. And actually, Eliashberg didn't show this, but it's actually a very easy consequence of what Eliashberg did. That very interesting fact that a contact structure is tight if and only if you have any upper bound on the self-linking number for any knot in the contact manifold. Interesting, but so again, transverse knots really come in an essential way in this fundamental dichotomy. And one thing that indicates why this dichotomy is interesting is because Eliashberg in his '89 paper actually showed that over-twisted contact structures, so ones that don't satisfy the Binnikin inequality, are in one-to-one correspondence with plane fields up to homotopy. Studying plane fields up to homotopy is very easy. It's just a little bit of bundle theory, a little bit of algebraic topology, very, very easy to work out. Again, if I was running fast, I was going to spend a little time telling you about the homotopy class of plane fields, but I think I won't, so that we can hopefully finish up on time. But again, this is actually very easy to understand, so it's saying that these over-twisted things are very, very easy to understand and really probably don't have any fundamental connection with, really interesting geometric topology of the three manifold. They're really more about the algebraic topology of the three manifold, so fairly weak information. But on the other hand, Binnikin's theorem says that the tight contact structures have some very interesting properties that I'll say more about in a second. But let me just say, I'm not going to go in details about the homotopy class of plane field, but let me just mention they're determined essentially by the Euler class of the plane field. So what's the Euler class? Just say, for instance, take a generic vector field in the hyperplanes, look at its zeros. That gives you a homology class. Its Poincare dual is the Euler class. And that more or less, together with something called a D invariant, determines the homotopy class of plane field. And again, I don't want to go into too much detail on these. But one example, at least, that I can show you is on S3, there's exactly a Z's worth of over-twisted contact structures. And they're basically, I'll denote them Cn. And the Cn's have this property that D of Cn is n. So basically, for every integer, you have an over-twisted contact structure. And just so you know my conventions, by the way, some people might be used to, in S3, these D3 invariants being half integers. I think it's a strange convention that got you to half integers because this definition works much nicer. Wow, different levels. So I'm using a convention that actually gives you integers, which is much nicer from many perspectives. But anyway, for reference, the standard contact structure has D3 invariant actually equal to 0. And anyway, the second thing that this is part of a statement I started over here. So Binnikin's theorem led to Eliashberg's work, but it also led to the fact that, that there's surprisingly subtle connections between tight contact structures and the underlying topology of the manifold on which they sit. In particular, you can use tight contact structures to get lower bounds on the genus of ciphered surface for knots. That's a notoriously hard problem in topology. I mean, nowadays we have tons of ways of studying that. But back in the 70s and 80s, this was a very, very hard problem that people really didn't know an awful lot about. And contact structures at least gave you a way of getting bounds on what that genus might be. So this is the first kind of indication that there was interesting subtle connections between contact geometry, at least tight contact geometry in dimension 3, and the actual topology of the manifold on which they sit. And since then, there's actually been dozens and dozens of other examples, well, maybe not dozens and dozens, but many other examples where contact structures have actually told you something interesting about the topology, and many fundamental results in the last decade have been about topology, pure topology, have been proven using the tight contact structures. So, this distinction between over-twisted and tight is really, really quite fundamental and really was born out of transverse knot theory. And again, I'm just emphasizing this over and over and over again because you can wonder, can something similar be true in higher dimensions? Okay. All right, well, let me give you a really, 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 really quick proof, sketch of the proof of Benneken's theorem. So just tell you kind of what goes into it. So what are the ideas? So the first idea is, notice that if you have a closed braid in R3, so what is a closed braid? Well, here's a picture of a closed braid. So it's an embedding of a circle, so a knot that's disjoint from the z-axis. We'll call that the braid axis, and such that the parameterization is such that the theta component is always increasing, right? So it looks like you've got some strands that have been braided around and they kind of close up on themselves. So that's a closed braid. And it's very easy to see that the closed braid is actually transverse to the standard contact structure, or at least if you make the r coordinate big enough. So you have your closed braid, you can increase the r coordinate enough. Once you do that, it's very, very easy to see that it's transverse, because remember the contact hyperplanes, as the r coordinate increased, they got close to vertical. And being close to vertical means close to the theta constant plane. So if theta is increasing, these are transverse. So given closed braids, you actually get kind of a unique transverse knot type. And the first thing that Benneken did in his work was he actually showed that any transverse knot can be written as one of these closed braids. And actually, this is a really beautiful result, but it's actually quite simple. If you know the standard proof, I guess, what was it, Alexander was the original person to prove this topologically? If you know one of the first proofs of how you can braid any topological knot, you can easily adapt it to braid a transverse knot. So it's a really nice result, but fairly straightforward. But you might ask, is something like this true in all dimensions? So if you have embeddings in higher dimensions, can you braid them? Well, first of all, that should lead you to ask the question, what in the world does that mean? What does it mean to braid something in higher dimensions? Well, we will be talking about that in the third talk, but maybe it's something you can puzzle on for the next 24 hours. But yeah, so we at least have a definition of what braiding is in higher dimensions, and you can ask, can you braid things? And that actually we don't know. Well, except in a couple other dimensions. So the second thing that Benneken proved, which is also quite simple, very, very easy computation, is that if you have a transverse knot written as the closure of a braid word, so a braid word just means, you see these just simple little crossings. Actually, I have a board here. Excellent. So you can do, if you have an n-strand braid, you have this very simple one where you just have this one crossing, and every braid can just be a concatenation of these, and then you close them up, right? Oh, that's hard to see? All right, let's see if this, any better? Any better? OK. Well, you can actually see that any braid is just a concatenation of things like this. And we call this, maybe I'd call this 1, 2, sigma 3. So you have these sigma 1, sigma 2, and so on, up to sigma, I guess, n minus 1 if you have n strands. And any braid can be written as kind of a word in these and their inverses, which means you just switch the crossing. So given a braid word that represents your braid, you can actually compute the self-linking by the algebraic link. That just means that if you have the generator, it's 1. If you have the inverse of the generator, it's minus 1. And you just take the algebraic length, and you subtract the number of strands you've got, and that's the self-linking number. So once you have your transverse knot as a braid, it's very easy to compute this simple invariant. OK, so these two are fairly simple results in dimension 3. Be great to have something similar in higher dimensions. So the hard part of Benneken's result is that given any surface for your braid, for your transverse knot, then you can find another surface that has Euler characteristic less than or equal to the original surface, and such that that surface actually has just the length of W, not the algebraic length, but the length of W minus n. And that's actually very easy, because if you have a braid, for each strand you take a disk, and for each crossing you put in a little one handle, a little twisted one handle. So it's really easy to see that given a braid, you can create a surface with Euler characteristic that. And of course, if that's the Euler characteristic, and that's the self-linking number, then clearly the self-linking number is less than the Euler characteristic of the surface that you created, but the surface you created has less Euler characteristic than that. Now, this is super sketchy, of course, just because this actually involves dozens of pages and very, very non-trivial analyses of kind of foliations or singular foliations induced on surfaces. And again, I'd be happy to sketch this for somebody, maybe during lunch or something if you're interested. But this would definitely take us probably a whole nother lecture at the very least to give a good sketch of this. So this is a very hard part. And unfortunately, this is something that is almost certainly not, you can't, these other things you can hope to generalize to higher dimensions. There's no way this argument works. Now, maybe some other argument works to give you some sort of Binnikin type inequalities in high dimensions, but there's no way this one will. Well, there's no way I could do it. Maybe somebody else that's smart enough to make it work. But I mean, the sort of problems you'd have to look at, the sort of singular distributions you'd have to look at on ciphered hypersurfaces would be so crazy that it seems really unlikely you could do anything serious there. OK, so good. Milestone 3. So we jump several years now. So contact structures can be characterized by equivalence classes of transverse fibered links. So this is essentially Giroux. Actually, it's Giroux plus a little bit of work that Jeremy and I did a while ago, which I'll get to later. But let me kind of start with the work of Giroux and Thurston and Winkelkamper. And it involves an important concept, which we'll come back to in the second talk, of open book decomposition. So let me give you one simple description of an open book decomposition. I'll give you a different one this afternoon. But an open book decomposition for manifold M is a pair, B pi, where B is just a link in M. That's easy enough. And pi is a fibration of the complement. So the complement of B is just a fibration over S1, which means the fibers are surfaces, right, because we're in a 3-manifold. And the fibers have to have a very special property that if you look at the fiber, well, the closure of a fiber, that its boundary is, oh, another typo, K is B. The boundary of the fibers have to be the link B. OK, good. So that's an open book decomposition. The B, this link, is called the binding, and the fibers, or the closure of the fibers, are called pages of the open book. And Thurston and Winkelkamper proved that if you have an open book decomposition, let n be a neighborhood of B, and they basically showed how on the manifold minus the neighborhood of B, well, you have the fibration coming from pi, and you have the tangents to the fibration, the tangents to the fibers. That's a plane field. It's not a contact structure. Remember on maximal non-integrability, it's not a contact structure, but they showed you can perturb those planes ever so slightly and make them a contact structure. And then they showed that you could just very explicitly take that contact structure here and extend it over the solid tori, the neighborhood of B, more or less by using the models back from fact 2 in Milestone 1. I think that's the right reference. So anyway, it's a very nice construction, very simple, nice construction that says, given open books, you have a contact structure on a 3-manifold. It's also a very easy result. Well, again, easy once somebody tells you how to do it, that every 3-manifold actually has an open book. So this is another proof that all 3-manifolds have contact structures. So one thing I'd like to observe, that because of the standard model here, you can actually easily see, well, sorry, I want to give one other definition first. We say a contact structure, this is a definition of Giroux, that if you have a contact structure, it's supported by an open book if there exists a one form whose kernel defines the contact structure. Remember, contact structures can be given as a kernel of one forms, such that the one form is positive along the binding, where you kind of use the orientation. There's a natural orientation on the binding. And D alpha is a 2 form that's actually going to be an area form on each page. Okay? So those are the conditions you want to have to say a contact structure is supported by an open book. And just a little bit of work past what Thurston and the Winkelkamper did, once you have Giroux's definition, you can actually show that there's really a unique contact structure associated with an open book that's supported by a given open book. Moreover, you can easily see inside of here from our construction that the binding itself is actually a transverse knot in that open book. So we have this fibered knot that happens to be a transverse knot in this contact structure. We need one other definition called stabilization, and since I didn't give you the other definition of open book, I have to give us what seems like maybe a slightly more complicated definition of stabilization, but I actually maybe like it better. So given any arc on a page of the open book, a neighborhood of that arc looks like that. So you've got your surface, and I've drawn the two boundary components that the boundary of the arc sit on. So it looks like that. Now what you do is you just take that arc and you kind of push it up a little bit, and you run a one handle along the image of that arc pushed up with a left-handed twist. And you get a new surface sigma prime. So the boundary of sigma prime is another link B prime, and it's a very fun and interesting exercise to try to prove that the complement of B prime is fibered with fibers coming from the sigma prime. And this operation of going from B and the fibration here to B prime and the fibration here is called stabilization. Okay? And now the amazing theorem of Giroux from the early part of this century is that contact structures on M up to isotopy are in one-to-one correspondence with open books on M up to stabilization and isotopy. So completely understanding contact structures is the same thing as completely understanding these kind of fibered links up to this stabilization operation. And these fibered links are transverse links. So in some nice cases, you might say that these transverse links really kind of tell you everything you want to know about the contact structures. Now from Giroux's theorem, that's actually not quite true, but I'll give you a statement about how it is true on a couple more slides down the road. I should mention that there is a version of Giroux's theorem in higher dimensions, but it's definitely much harder to work with. But you know, people are thinking quite a bit about it, and maybe in the near future there might be interesting things like I'll talk about in the next few slides that you might be able to do in high dimensions as well. Okay, good. So now I just want to mention a few other kind of more miscellaneous results. I don't think I'd call them milestones in contact geometry. Those other three things were fundamental developments that our current state of contact geometry would not be the same as it is if any one of those three were missing. Now I'll just give you some nice results about transverse knots and their classification, a little bit about their structure. And again, these are all things that you might think, can we mirror them in higher dimensions if we try to look at contact embeddings in higher dimensions? So let's see. Good. So the first thing I want to mention is that all contact structures can be realized as branched covers over transverse knots in S3. So I'm actually going to talk a lot about branched covers in the first talk tomorrow. So I don't want to go into details, but branch cover just means that it's an ordinary cover in the complement of some kind of singular locus. So it's kind of like a singular covering space. And again, we'll talk a lot more about these next time, but it's a really nice way to think about three manifolds. And it turns out that every contact structure is just a branch cover over some transverse knot in S3. And an example is if you take the 2p torus knots, and you take, that's a braid, so remember that gives you a transverse knot. If you take the branch cover over theirs, you get a standard contact structure on a particular lens space. Again, if you haven't ever thought about these before, it probably doesn't mean much to you, but it's just an example of how you can build a contact structure from a branch cover. And you can get everything that way. Well, and again, very interesting question. Can you construct all contact structures in high dimensions by branch covers over contact submanifolds? And well, the answer to that I can give you right now, it's no. Because it's actually known, as soon as you get to dimension, I can't remember if it's 7 or 8. So for contact manifolds, either 7 or 9, there are actually manifolds of those dimensions that are not realized as a branch cover over the corresponding sphere of that dimension over an embedded submanifold. You actually have to use some embedded complex to kind of get the branch cover. So there's no way that you can get an exact analog, but the question is, well, is there something similar that you could do in high dimensions? And that might still be true, but I actually have no idea about that one. But very interesting question, I think. OK, what else can we say? So are transverse knots completely determined by their topological or smooth knot type and their self-linking number? Well, that actually was an outstanding question for many, many, many years. It resisted many, many, many different attacks. But finally, in 2005 and 2006, There were counterexamples given. Actually, both of these appeared about the same time a few years earlier, but they were published in 2006 and 2005. So the first couple of examples, the first set were given by Bierman and Manasco, where they have closures of 3 braids, in particular these 3 braids. These have the same self-linking number, but as transverse knots, they are not transversely isotopic. The proof that they used was actually very, very involved, and it involved, again, using ciphered surfaces and analyzing the foliations induced on those by, well, the braid structure. And it's actually very, very, very reminiscent of Binnikin's arguments. I mean, very, very parallel to the sort of things Binnikin was doing. And Bierman and Manasco managed to prove this nice result using those ideas. And then Kohanda and I managed to just explicitly classify transverse knots in that particular knot type. And we actually showed that there's 2 representatives with self-linking number 3 that are not transversely isotopic. So the technique there is just, well, classify everything. Instead of answering a simple question, answer a more complicated question and get some corollaries. OK, so let's see. We've got 2 minutes, dozens more slides. No, it's not that many. A few more slides, but we might go a little bit quicker now. So what about classification of transverse knots? Remember I said they had an interesting structure. So for instance, you can ask, can I completely understand transverse knots in various knot types? The first result along those lines was in 1993, and Eliashberg classified unknots. So you look at all transverse knots that are topologically the unknot, and he showed that there's actually, for every odd integer less than or equal to 1, there's exactly 1, and they're related by an operation called stabilization, which I don't want to define now, but it's just one way to take a knot, say with self-linking number maybe 1. When you stabilize, you get a transverse knot with self-linking 1 less. So what you could say here, Eliashberg's result, is there's kind of this unique kind of maximal self-linking guy that, there's a maximal one because Binnikin says they can't keep getting bigger. So you take this unique maximal one, and everything else is just a stabilization of that. And then there was a series of generalizations by lots of different people that said for many, many other knot types, you could prove a very similar result to Eliashberg, that kind of there's this one unique maximal guy and everything else is just a stabilization of that. So torus knots, figure 8 knots, positive and negative odd twist knots, various cables. And I think there's one more result I wanted to mention there. So also Bulent also proved that various negative and positive cables of torus knots. So there's lots of examples where you just have this very, very simple picture that you have this one maximal guy and everything else is a stabilization of it. OK, what about things that maybe aren't so simple, where the self-linking doesn't determine it? Well, the first such example was by Koh and I, where we said this 2-3 cable, a 2-3 torus knot. That's exactly the one I was showing you here, right? That one, that knot. I hope I got it right. Left, yeah, I think that's right. That knot, the classification is exactly this. So you have this one maximal one, and everything down here are stabilizations of it. But then you have this one here of self-linking 3 that isn't related to those, but as soon as you stabilize it once, it becomes the same as the ones that are coming down there. So you just have this weird thing that shows up, and you've got this one extra one showing up. You also have this interesting behavior here. Generalizing this work with Koh, Doug LaFountain and Bulent Tosin and I showed that for other cables of positive torus knots, you have this, you have this unique maximal one. You stabilize it k times. You just got this 1, 1, 1, 1. But then all of a sudden, n show up. So there's n minus 1 extra ones that show up, and they remain distinct as you keep stabilizing for L times. And then you stabilize after that, and you get one more. So now you've got n, one more on top of the n before. You stabilize m times, they stay different, and all of a sudden, they all become the same. So anyway, so again, very interesting behavior that kind of shows up here. And also the negative even twisting twist knots you can classify. So the last thing I'd like to kind of mention here, and I guess we're 1 minute over, so it has to be very quick. Last thing was I was alluding to this result of Jeremy and mine about using transverse knots to classify contact structures. There was kind of hints that this was true for actually since the beginning of classification results. And I've been trying to find a way of phrasing it for a long time. And finally, Jeremy and I came up upon this following theorem on the next slide. But first, let me not go through all of this. Let me just look at this thing right here. What is script T, C, N, K? This is all of the transverse knots in the contact structure C in the knot type K with self-linking number N. Okay? So you fix the knot type, you fix the self-linking number, and you look at all the transverse knots up to transverse isotopy. And it turns out you always get some finite set here. Well, in in a tight contact structure. You get a finite set there. And notice that you can use these sets to actually tell whether something is tight or not. Because remember, something is tight if and only if there's a bound on the possible self-linking numbers, which means something is tight if and only if, when n is large enough, these sets are empty. So you can use transverse knots to tell whether something's tight or not. But better, Jeremy and I managed to prove that if you have two different contact structures on a closed 3-manifold, then they're the same contact structures, isotopic contact structures, if and only if the cardinalities of these sets is the same for all n and all fibered knots. Actually, you don't even need all fibered knots. You can take some subset. But yeah, so by understanding the fibered knots in a contact structure, you completely understand that contact structure. So that's really telling you contact structures really see everything you'd ever want to know about a contact structure in some sense. Now, making this explicit is very, very difficult. But I do want to mention that it's not too crazy. In some examples, for instance, on T3, if you already know C and C prime are tight, it only takes 3 knots to completely specify what the contact structure is. Well, 3 topological knot types. And then understanding the transverse knots in there, you then completely understand the contact structure. And it's probably true that if you're willing to stick to the tight setting, then you only need a finite number in general. But I actually don't know how to prove that. But if you're looking at all contact structures tight and over-twisted, I think you always need an infinite number. You probably always need an infinite number of knots to tell things apart. But I also can't prove that. But we can prove this, that if you look at all fibered knots and all integers, then that does actually classify things. So again, you might ask, by studying contact submanifolds in high dimensions, can you actually completely distinguish and classify contact structures in high dimensions? And well, we have no idea there. But again, very interesting question, and I think that's a great place to stop. Thank you. Yeah.
I have a question on the last result that you just mentioned.
Uh-huh.
Do you have to already understand the classification of contact
No.
to get an explicit list of knots?
Oh, to get an explicit, yeah, if you want to get an explicit list, the only way I know how to do it currently is if you already have a classification. I think on every manifold we have a classification. I can give you a list of knots that you can use if you already assume it's tight. But a priori, it's not entirely clear that has to be the case. But certainly that would be the easiest way to do it. Yeah. Yeah. Yes. So you get there are 3 knots, and then if you hand me 2 contact structures that you already guarantee me are tight, then if I just kind of check these cardinalities for those 3 knot types, you're done. Yeah. Yeah, it wouldn't be very interesting if I had to pick the 3 knots after you gave me the contact structures. Yeah.